And in my talk, I'll focus on the importance of next-generation semiconductors for sustainable electronics and sustainable industries. And semiconductors, of course, are the materials that define our civilization progress in the last century, in this century. They continue to enable advances in practically all scientific endeavors, and they're transpiring as key materials to enable the transition to green energy and to preserve the Earth's livelihood for future generations. So we have had wonderful talks in the morning about the importance of semiconductors for their role to enable solar power conversion to electric energy, also other energy sources. Semiconductors are also at the heart of modern communication and information networks. They have enabled solid-state efficient lighting, different type of sensing applications, information storage, generally digitalization. And one very important aspect where semiconductors are also key is to contribute or practically enable the transition to efficient energy system when it comes to electrification of mobility and also power conversion, power utilization and transmission. And these are the aspects that I would like to focus a little bit more in my talk. So we as civilization consume a lot of energy. Here you can see I've taken this statistics from the EU Council showing that in 2022, EU used or totally generated about almost 2,800 terawatt hours. So this is huge. And that's the distribution of different sources, quite a bit still on fossil fuels, a lot of the renewables, and some percentage of nuclears. Of course, we are all working towards getting this here totally green in renewables. But one main problem, independent on how we get energy produced, is that we have a lot of conversion losses, and you can say that's a hidden tax to electricity. And these losses, they are on average estimated to be about 10%. They can be, of course, dependent on the application or way of operation, can be a bit lower, about 5%, but also can be significantly higher, up to, for example, 30%. Even taking this average number of 10% from the EU total generation, we then end up with a number like 280 terawatt hour, which is a huge number that goes into losses. It's just wasted. And if you want to compare, for example, this is quite large number, significantly higher than, for example, what's the annual production of electricity in Sweden, and then you can say it's equivalent on amount similarly to what is the electricity production in countries such as Italy and Spain, if you want to get a taste of the amount of losses that we are dealing here. And what are these conversion losses? So every time you use an electronic device that is connected to a main supply, you have to convert from alternating current to DC, so in the computer, television, so right there you lose about 10% of the electricity. There are also conversions from DC to AC. For example, your solar cell generated DC has to be inverted to AC to be used in the house or in all small switch power supplies for a computer, to adjustable speed motors, for example, in hybrid and electric vehicles, and so on. There are a number of other type of conversions where, for instance, DC to DC, AC to AC, where, for example, you want to maintain the voltage, or you want to adjust the level, for example, in light dimmers and so on. So this is really ubiquitous. It's a lot, and it's a problem that has to be dealt with. And as you could easily imagine, the future doesn't look brighter from that perspective. So we will consume more power. So this is in the world, and this is a projection now by 2050 in Europe. This number raises up to almost 5,000 terawatt per hour, or that's an increase of 40% or almost doubling from what we are using today. So we have to deal, conversion is inefficient, and we have to deal with this problem. The way to do it is to improve all the power electronic components that are used. So up to date, for example, we use 70% of all electricity that is produced goes through a power electronic component. So, and if we would like to increase or reduce the losses, we want to increase the efficiency, so you would like to have a good switch, which means that in the off state, you want to be able to hold a lot of voltage, so this should behave as a regular insulator. And then in the on state, you want that to have very low resistance, or that your switch is a good, behaves basically as a metal. And here is a comparison of different material systems. So you want to have small resistance, high voltage, so you want to be in this corner. And gallium nitride is one of the next generation semiconductors that can enable such better electronic switches. So let's look a little bit more into detail into the properties of this material. So this is silicon as compared to gallium nitride and other wide bandgap materials such as silicon carbide. So one property that is very important is the electron mobility. So what is an electron mobility? That's the ability of the electron to travel in the crystal. And then for low resistance, we want as high number, as high mobility to reduce the resistance and the losses of current flows and respectively. So you can see here, this is a large number for gallium nitride, 2,000 as compared to 1,000 for silicon, even lower silicon carbide for the on state. For the off state, you want to hold large voltages. That means that you need to have a high critical electric field, or this is basically the electric field that you can apply to the material before it breaks. Again, gallium nitride has, say, 7 times larger than the breakdown field of silicon. So if you want to combine the high mobility for low resistance and the high breakdownage for withstanding in the switch, your answer is gallium nitride. And there are also other parameters that are important and, for example, can enable these so-called wide bandgap materials as gallium nitride and silicon carbide to operate at higher temperatures, therefore reducing also thermal losses, reducing the need of cooling or getting rid of cooling entirely. And that means that you can get the component or the whole package smaller, and smaller mean chips, and that's of course a way to penetrate a market and contribute to a better economic impact. So we take now the gallium nitride, and what do we do with it? So how do we make device? So we basically use exactly the same concept as for the silicon MOSFET transistor. So this is the main engine of industry today. So it's a huge industry. This is what you have in your pockets, in your laptops and so on. Silicon is everywhere, ubiquitous. So you have source of electrons, you have drains of electrons. Your electrons travel from the drain to the source, and they are modulated by the gate that switches off and on your power switch. And now the same concept here is developed for gallium nitride high electron mobility transistors, or HEMT, where you form a sheet of two-dimensional electron gas at the interface between the gallium nitride and AlGaN, and that is without any doping. And now these electrons in this two-dimensional electron gas have a very, very, very high mobility, and they travel much faster. They lead to low resistance and low losses. And they also, these HEMTs are capable of withstanding high electric field. So what's the potential, the saving potentials if we look into 10-year perspective by using gallium nitride? So there are different sectors in industry that are responsible for the energy consumption, and you can see quite a lot can happen here for motors and heating, ventilation, and AC. Also a big number associated with ICT and computers, renewables, and their role will be increasing in the future, and also electric mobility. So all combined, this is now an estimate of reduction of losses by half. So the potential of gallium nitride amounts to 1/2 of the EU annual energy consumption. So imagine this is tremendous, and this is very important because power sector is one of the more it's having a high impact also on environment. It's one of the most intensive CO2 emission sectors, and if we and EU also is among the world's top CO2 emitting power sector. So last year, this is just above 700 megatons of carbon dioxide that we are talking, and that's about 6% of the world's total power sector emissions. So if we get back to the numbers of savings we can get into from gallium nitride technology and convert that into CO2 reduction, you can see that this also is a significant amount. This is, of course, a rough estimate, about 360 megatons by 2033. And for example, huge amounts from renewables. And this is not what you can save by using renewable energy. This is not the reduction in CO2 emission because you use renewable sources. This is only tackling the conversion losses. So this is huge. If we take a larger perspective, let's say not 10 years, 50, 100, so this goes to 10 gigatons and above. So it is really important, and gallium nitride actually covers a large range, so its technology is not only covering a specific area, but a lot of power ranges from wall plugs, charger adapters to consumer for gaming PCU that's already on the market. Very, much smaller, much more efficient in terms of energy consumption. Big impact is expecting also on DC-DC onboard charger, drivers in the inverter, where silicon carbide and other wide bandgap materials has penetrated already, and gallium nitride can contribute as well in electric 2-3-wheelers and consumer electronics and so on. So really, a huge impact where traditional systems can be replaced by next generation of compact and efficient systems based on gallium nitride devices. Another area that is very important is connected to where gallium nitride technology has a huge impact and potentially have even more stronger impact in the future is the power amplification or the power infrastructure at millimeter waves and high frequencies. So we are now moving from 4G to 5G and looking into 6G, and 6G is about hyperconductivity. So we need, this happens at a much higher frequency, 95 gigahertz and above, moving from what is 5G already base stations based on gallium nitride are in fact deployed, and moving completely away from the 4G. So what do we need? We need a lot of bandwidth, and the transistors have to be with high gain, high power, withstanding high currents and lower leakage currents. And why is this important? Because if we can handle high power at these high frequencies, so one can make the base station smaller. And this is important because in the 6G scenario, we are not dealing now with a base station every 1 or 10 kilometers. Well, will be emerged into a sea of small, efficient base stations that will be probably at every light pole, if you think. So gallium nitride, thanks to this 2-dimensional electron gas, large charge without doping, provides the highest output power, as you can see at this high frequency, in combination with the large breakdown voltage due to the wide bandgap. And of course, it's all sounds nice, but there is really a lot of challenges to be solved both on scientific and innovation front to move forward this technology and improve it further. And it has been discussed quite a lot in the morning that there are key words that were mentioned in the high-level discussion. So that was the collaboration and also having the work with industry in a close way. This is exactly what we do here in the Competence Center for Trinitride Technology, Zenith, where we develop next-generation power and high-frequency electronics. So all these aspects that I mentioned earlier in my talk based on gallium nitride. And we do that in a close collaboration with industry, and we aim at enabling cost-effective increase of capacity and efficiency in communication, power, and sensing systems, and therefore addressing all these important societal challenges. So I mentioned the digitalization, electrification, sustainability, but also defense and security. And I cannot emphasize less how important is this, especially nowadays geopolitical realities. So one very important thing I would like to point out here, where I do believe we are quite unique, is that we really cover the complete value chain. I haven't heard on a world scale of other activities related to gallium nitride that has all of this. And this also has been mentioned because we need to be faster. So faster was another word that was mentioned in the discussion in the morning. And to be faster, we need to be able to cooperate in a good way from the people that create the equipment to fabricate the material, processing devices, reliability models, and systems. I don't really have the time to, I guess, go into too much details. I have planned for 30 minutes. That was my bad. I'm sorry. So, but I just want to tell you, I don't have much science, but this I can give you right now. So we have been working very hard on the lateral devices, and these are some examples of state-of-the-art. So you remember this graph, low resistance, high voltages, still way to go to reach the gallium nitride limit. So a lot more to be done, but I think we have been doing great. Also integrating with our industry. So if Ericsson and Gottlieb comes to me and say, we want to go to high frequency, and then we identify this technology, then I can actually go to the material grower, do it, and even talk to the producer of the equipment and ask him, do this modification for me because we want to have this impact. And this is now going from the lab to the UMS, European leader in RF market, in improving output power and reducing leakage current, again, efficiency. So I wanted to mention, can you allow me 1 minute? I just would like to highlight something that I promised to my colleague Lars-Erik Wernersson, because, I mean, I'm coming from the gallium nitride world, and of course this is very important for me, but that's not the only problem that we need to solve. There are other issues. Quantum was mentioned, also low power, neuromorphic computing, and there are large activities here at Lund University on taking more standard 3.5s and combining them with CMOS that can go to a lot of innovation, for example, with also, you can see here, a huge energy saving demonstrated by in-memory computing solving a long-term bottleneck. We also are looking towards establishing a national semiconductor agenda together with our colleagues at the different university and funding agency, and also building infrastructure where we can use to join our forces between different technologies and address societal challenges and also industrial challenges. So thank you very much for your attention.